If a force on an object is varying over time, we can find the work done by that force by looking at a certain graph. So consider here our gem that is tossed up in the air on a windy day so that there is a constant force of gravity on it, and also simplistically a constant drag force from the wind pushing on it. If we were to graph the net force on the gem in the x direction as a function of position x, as the gem moves towards the right, so it moves in the x direction, and say it was a 3 Newton drag force to the right, so a positive 3 Newton drag force as the gem moved from moment 1 to moment 2 here. So it moved from x coordinate x1 to x coordinate x2 over that time period. Then this cyan colored area here of this rectangle, that area would be the delta x, the length here, times the width, 3 newtons. So that area is the net force x component times delta x. Likewise, in the y direction, if we graph the net force in the y direction as a function of the y coordinate, of the y coordinate of the gem, with a negative 4 Newton force of gravity as the gem moves from 1 to 2. So the gem has a delta y here equal to that value. So the delta y would be y final minus y initial. So this delta y times the net force y would give us the area of this magenta colored rectangle. Net force y times delta y. And we're accustomed to the idea that an area that is underneath the zero axis like this counts as negative. So the area of that rectangle would be a negative value. But looking at these two expressions, net force x delta x and net force y delta y, we are reminded of work formula number 2. Because fx delta x plus fy delta y, that is the sum of the products of the parallel parts, that is exactly what we mean by the work done by that force. And so net force x delta x added to net force y delta y would be the net work done on the gem from moment 1 to 2. In other words, the net work on the gem equals the sum of these areas. The area under the force versus position graph looking at x components, plus the area under the force versus position graph looking at y components. So area under a force versus position graph is going to be related to work done. It's going to represent work done for us, and that's helpful. That's most helpful if our force is varying over time. So here's our principle. For an object moving in 1D in the positive direction only, so we're really restricting ourselves to a small subset of scenarios, but a relevant subset. An object moving in just 1D in the positive direction only, the work done on the object by a varying force equals the area under the force versus position graph. I've got a scenario for you to consider and then a practice problem for you to do. I think you'll be able to work it out just based on this concept right here. Here's the scenario. Suppose we toss the gem on a gusty day where the wind is not blowing with a constant drag force, but a drag force that's changing dramatically from moment to moment. So here's the path that the gem takes on this gusty day. We can see it carried rapidly to the right by the wind, and the wind dies, then the wind picks up again, it's pushed more to the right as it falls. We have a constant force of gravity throughout the whole story. That's not changing, but our drag force here starts small to the right, gets big to the right, then shrinks and actually reduces and flips and points to the left for a time, then reduces and flips and points to the right again and gets even bigger. So you have a highly variable drag force on the gem as it moves from 1 to 2. And let's just look at the horizontal motion of the gem, the change in its x coordinate over time, since we're only considering objects moving in 1D. So we'll ignore the vertical movement and just look at the horizontal motion here. Here is a graph of the x component of the drag force on the gem due to wind as a function of the gem's x coordinate, the gem's position horizontally, assuming that at time 1, right here at moment 1, the gem is located at an x-coordinate of 0, and by the time the gem gets over here to moment 2, it's located at an x-coordinate that's just under 8 meters here. And so here in red is the varying drag force from that wind. Our principle is that the area under the force versus position graph represents the work done on the object by that force. So I would like you to use that graph to compute the work done on the object between 1 and 2 by the varying drag force. So we're going to call that WD, big W subscript little d, the work done by the drag force between moments 1 and 2. You'll pause the video in a moment to do this, but I have a few tips for you. Tip number 1, break the areas into triangles and rectangles, and then add them up. Tip number 2, check the scale on the horizontal and vertical axes. Axes sometimes have different scales. Check before you put in numerical values. And tip number 3, any area below the fx equals 0 line is going to count as negative work. Okay, that should be sufficient. Pause the video now and compute the work done. Ready? Answer can be found as follows. The work done by that varying force is going to be equal to the area under the force versus position graph curve during that time interval. So we are going to break up all these areas into rectangles and triangles and add those areas up. Note that our scale on the horizontal axis is different than our scale on the vertical axis. Looks like vertically each square is worth 1 Newton, but horizontally each square looks like it's worth 0.25 meters. So being cautious about that, we can find these 3 areas as one way of breaking up this shape. There are other ways of breaking up this shape, but the sum of all those areas should come out to be the sum of these 3 numbers here. Then we have these shapes here, adding up to those values. There's no work being done during this portion of the story right there. When the drag force disappears temporarily, there's no force, no work. But then when the force reverses to push to the left, so we have a negative FDX during this time, that's doing negative work. So here we've got the wind adding kinetic energy as it pushes the gem to the right. Then here the wind is removing kinetic energy, doing negative work as it pushes temporarily to the left. And then it adds kinetic energy again as it continues to push to the right. Adding up all these energies, counting this one as negative, the work done by drag is the sum of all those areas, comes out to be 26.625 Newton meters, a positive number, net positive work, indicating that the wind transferred a net kinetic energy to the gem, speeding up the gem over that time interval.